Yeah.
like I guess was a lot of them. Maybe I should spend a little less time with others. But then I was like, okay, I could figure this out if I had more time, but I didn't have enough time to think and write. And then I was just drawing. I was just pulling shit out of nowhere, to be honest.
Well, and I mean, I
Because I was
think
like, I
that's
don't know how to make this work, and I might as well write something down so I get some, maybe a possible quarter of a point.
that's the thing. Like, I've never felt comfortable with the time on an OCHEM exam. It's always like, oh, if I had more time, I would be able to get a better score. So part of it is like the time stress of it, and that's why the practice exams and doing them in that kind of timed closed book is so important to prepare you for that, to get into that mode. Well, how did y'all feel about the like questions on the exam versus like the practice
I
exams?
thought practice exam A was so much easier than the exam, and I thought
Really?
it was like kind of like the exam, but really
I agree. I agree.
I think of the three, B was the hardest. Yeah.
There was more
Um,
tricks in B.
yeah.
Like B, there was like more things in
we asked you about like polarity out of the blue.
Yeah.
and like the ketone being thrown in as like a reagent.
Yeah.
And it was,
Yeah, well, and this is the thing. The practice exams were not made to just be practice exams. They were the exams that we gave in past years. And so it's interesting to see how it kind of changes year to year. Like, my assessment of it is I think that the hardest question this year was the mechanism. I think our synthesis was easier than normal. I think the first, like, page, like, hybridization and functional groups, that's kind of on y'all. And so if there's something missed, I take no responsibility for that page. The other pages, I take some responsibility. I thought that one of the resonance structures was weird, but the rest could have been pretty easy to figure out. Ranking acidity and just give us a pKa value seemed pretty straightforward in my mind. The line reactions, one of them was hard. It was the one I wrote. The B, the one that has the cyclic ester and the ketone. So yeah, that one was harder. Apologies for that. It's a rough one. But yeah, I think that like in my mind, it feels like an overall pretty balanced exam of like some parts a little easier. Like the MO question, I thought was really straightforward this year, and so making the MO and like the synthesis a little bit easier and making the mechanism a little harder was kind of like the trade-off thing that we're balancing. What other thoughts do people have about the exam? The what? Yeah. Well, I remember first time I saw the like left versus right OH one, I was like, that's a little nuanced.
Terry just lied to me over and over again. Personally.
I've been enjoying.
But you're not a
lectures.
curious.
I'm not. I think that it's a fake system, and to tell you that's a system that works is to lie to you. It's a like framework for if you have no framework, it is something to latch onto, but it is a tool and is not definitive. Yeah.
You know what about like?
I'm gonna go through the timeline.
Okay.
Yeah. I want to ask like two questions, and these are kind of the big things that I'm concerned about when like helping to develop the exam. One, did you feel like you knew what was going to be expected of you, and you knew what the format of the exam would be, and like what you were responsible for knowing? I'm seeing nods. Can I do like thumb meter for like agree, disagree? Okay. And then the other one was, did you feel like you had comparable problems and difficulty to help you prepare for it? And then I was going to add something else, but yeah, did you feel like you had comparable problems with the PSET and the practice exam to prepare you for the level of difficulty on the exam? So, for those of you who have more down, what would you have liked instead? Would you have liked more practice exams?
Yeah, I just don't think there were a lot of problems. Like, I feel like the ones we had were similar. But
Specifically for like one type of problem, like for like lecture 3 stuff, or?
yeah, maybe like the box reactions.
Hmm.
Yeah, we didn't see those in the PSAT.
They were in the PSET, on PSET too. Yeah, but I think that they were like skill
Oh,
builders.
yeah, but we didn't have any like reaction product ones.
Mm,
We just
okay,
had the,
that's a
like,
good
put in
point.
ingredients.
I ran out of practice problems when I was done.
Yeah. Well, and the thing that we have to kind of balance is like, we don't want to overwhelm y'all with things because we're already giving you so much with the problem sets, and then with 2 practice exams and like a 5-day period to do them. Like, I think that for the students who did work through all of those and did kind of were able to kind of budget it and had the time, then yes, you want more resources. But for the students who were like barely getting through 1 to 2 practice exams, then it's like, oh my gosh, I didn't do all this other stuff that I should have done. And so it's a balance, but I agree with you, especially for the box problems like line reactions. I think that needs more. Cool. Other thoughts before we kind of move on? I'll tell you about the timeline. A lot of sad looks. So we are going to be done with grading Sunday night. On Monday morning, we're going to get together, the like teaching staff, and we're going to look at the data, and we might like adjust point values for like errors that we've done, or like, for example, like if I'm grading something, I call something a 2-point mistake on a 4-point like sub question, and like 30 people miss it, we might make that a 1.5 point mistake or something, like because it was so common that maybe we shouldn't have counted off as much for it. And so we're going to make some kind of little tweaks, look at what the averages are, and then we will probably post the grades Monday night. And at the same time we post them, I'm going to post the answer key. The blank version is already on Canvas if you want to see it for any reason. I will also be sending out an announcement to be like, hey, grades are out. And the announcement will have some details about regrade requests. So regrade requests will be due next Friday. And regrade requests have to be for a valid reason. Things that are not valid are, I think I deserved more partial credit for this. Thank you. Things that are valid are, hey, the answer key is what I put, and so you graded this wrong. Or things that are like, hi, based on these references I'm pulling from the material I was given, this seems like a reasonable way of doing this, or I think that this is a valid approach. Which case, like, I don't want to say it's often not, but it's often not, but it's engaging with the ideas, and it's like one done in good faith rather than the like, you should have given me more points here. So that's kind of regrade requests. The thing I will encourage all of you to do with this first exam is take it as a diagnostic, not so much of your mastery of the content, but a diagnostic of your study methods. Because before exam 2, you do have time to adapt and change things that are not working. Between exam 2 and the final, you will not have time to change. Like exam 2 is 1 week before the final, and by the time you're there, you're not gonna reinvent your study approach. And also a lot of your studying for exam 2 is basically studying for the final because they're so close. And so I think another kind of big thing that happened this week, really, within maybe 1 or 2 days before the exam, or sometimes in the exam, I think that y'all got a much better idea of what the game is in terms of like the OCHEM exams and the type of questions that we are going to ask you. And also, I think that by studying for this exam and seeing what went well and what didn't went well, you saw what you needed to do or should have done to study some of these types of questions for your own personal method. Because everyone kind of comes into the OCHEM class doing their own studying strategy that they've worked in the past, but this exam will highlight the things that are not working in that study method. So I would encourage you to take it more so as a chance to kind of reflect and make some changes, and or see what like is working. Like what parts did you nail? What parts did this type of studying really feel effective for you? And then, yeah, I don't worry too much about the grades. Like the first exam's only 15%. And I know many students in the past who have had a rough exam 1 and then come back with a strong exam 2 and final. I've also known many students who had a strong exam 1 and then a rough exam 2 and then a mid-final. Like there are lots of different trajectories. And very few people fail this class, actually. So, cool. Any questions before we jump into lecture or up section? Oh my gosh. Cool. Okay. Well, we have like 4 big topics that we're going to try to get through or touch on some today. We have amines, enamines, we have redox reactions, the carboxylic acid derivative or CAD family reactions, and then amino acid chemistry, mostly with those protecting groups and everything. Cool, so let's jump into it. So first off, with amines and enamines, we have some functional groups. These are new functional groups. Now, we are not going to have a new question on the exam that's going to like ask about these functional groups. These are not going to like appear in the final as something you have to circle and identify. But for studying these reactions, it will be very useful to have language to talk about them. And I think that you've started to see that with studying of like identifying functional groups when you're trying to do a line reaction or a synthesis is important. So we essentially have like the nitrogen flavor of some things that we've already seen. So a carbonyl here was a carbon-oxygen double bond, and the nitrogen flavor of that we call an imine here, imine with an I. Now, one thing that we saw kind of in passing was this thing called an enol, which is like an alkene and an alcohol. So we call it together an enol, and it has some resonance going on here. So the amine version of that is an enamine. Oh my gosh, cute. Enamine. So these are kind of our two main like nitrogen flavors. You also might think back to section 2. Do you remember we talked about like primary, secondary, tertiary amines and kind of introduced it? Well, that came back for these reactions, and specifically we're going to be talking about primary amines, which are amines that are attached to one carbon chain, and secondary amines, which are attached to 2 carbon chains like this. Now, if we protonate an amine, it becomes an aminium. I know that seems like a small distinction, but this is like the name for like a protonated carbonyl of a carbenium. IUM generally just means positively charged. And so if you want to think of these as pretty interchangeable, you can, but I will say imine and iminium, and I don't want you to get confused. The other one, this is my favorite one. This is called a hemiaminal. So the amine is from like having an amine here, and hemi is that prefix that says that there's an OH, just like a hemiacetal. And I remember exactly where I was when I first heard this word. I was in Science Center on the 2nd floor at a review session for Chem 30, and the TF was talking about this reaction and said hemiaminal, and my gut response was to just go, gazoom tight, because hemiaminal sounds like an involuntary utterance. It sounds fake and made up. I truly like checked out. I put my pencil down in that moment. I said, this is fake. What are you trying to do here? What game are you playing? And now I just think it's really funny. This is also the neutral intermediate that you're going to form in these reactions. And so it's good to be able to kind of spot her and to be like, oh, yes, I'm doing this ridiculous thing. Cool. We have one other kind of nomenclature notation thing here. And that's about the positions relative to our imine or carbonyl. So these are also true for if we have a carbonyl. But here, if we have a CN double bond, the carbon one away from our double bond carbon is called an alpha carbon. And the hydrogens on those alpha carbons, we would call alpha hydrogens. Similarly, if we go, instead of 1 carbon away, we go 2 carbons away, these are beta carbons, and the hydrogens on them we would refer to as beta hydrogens. It's kind of this like relative position like label, and this is going to help us with some language of like summarizing sub-steps in a couple minutes. Cool. Any questions on the new functional groups? Yeah, Elisa. One away from the carbon and the imine. Cool. So, the big idea with the imine and enamine reactions that you should take away is the type of amine, either primary or secondary, that you use will determine which product you get. So, if you start with a ketone or aldehyde and you add a primary amine, one with only 1 carbon chain, you will get out the imine, the CN double bond one. So this is our primary amine, makes an imine. And then if we start ketone or aldehyde and we add a secondary amine, we will instead form an enamine. So part of this has to do with like primary amine versus secondary amines, they have different numbers of hydrogens on them. So like if we tried to make a imine with a secondary amine, it would look like this, and it would be stuck with a positive charge. And so we are going to do a step here to turn it into the enamine so it no longer has a positive charge and it's neutral. Cool. When you're thinking about line reactions, as we should with pretty much all new reactions going forward, be thinking about little fake mechanisms. Like, what would be a fake mechanism to go from an enamine to a ketone aldehyde? Yeah, I might like reframe it slightly. Like, yes, anything that you can do to write it, I would cut this and then put a double bond to O. And that's for if I'm going this way. If I was going this way, what I would do is I would erase this, make a single bond to my R2N, and then put a double bond to the side. Again, just be kind of constantly thinking about those as tools. So the mechanisms for both of these are really similar, and I'm not going to do like a super deep hash of it, but I am going to talk through it. So you start off, the amine attacks the carbonyl. You don't protonate the carbonyl first. When you do that, you are going to get to a tetrahedral intermediate, and this is where we can start using proton transfer. So we are going to proton transfer this charged, doubly charged molecule to the neutral hemiaminal, gesundheit. So once we are here, we need to think about, okay, what is our goal of our reaction? Well, we are trying to kick off the oxygen completely. Like in both of our products, we don't have an oxygen anymore. Oh, there's a typo. I'm so sorry. You see this like hydrogen that I'm like blocking out? That is a typo. It's a like notation thing where like when I type in like R2, it gets funky and starts to try to add hydrogens to things, and I can't control it. But yeah. Anyway, we got to the neutral hemiaminal. We want to make this O leave, and so we need to protonate it and make it a better leaving group. And I've shown that protonation by taking a hydrogen from something on the solvent, and this is just kind of a generalized version of it. If you wanted to like use H2O, that's totally fine because this is an aqueous solution. Then we now have a good H2O leaving group, and we can do a lone pair push from our nitrogen, kick off H2O, and then we form an iminium ion of some flavor. So all of this is the same for both of them, whether these R's are carbons or hydrogens, but the final step depends on whether it's a primary amine or secondary amine that we started with. So if we started with a primary amine, we would have a hydrogen here on this iminium that has a positive charge. And so to finish off the reaction, all we would need to do is deprotonate that and make it neutral. Easy peasy. It's kind of like the final step of an acetal reaction. But over here, if we start off with a secondary amine, we are going to have two R groups here. We don't have a proton that we can easily remove from our nitrogen and make it neutral. And so what we do instead is we look at the alpha position right next door to our carbon-nitrogen bond, and we are going to do an alpha deprotonation. This is kind of similar to some arrows that you saw with like conjugate addition of like 1,4 addition. When you do the mechanism of that, you have like an alpha carbon protonation, and this is just doing a deprotonation at that position. And when we do that, we will push up and make the amine neutral and wind up with an enamine. Questions about this mechanism? This reaction, or both of these together, you're really just using the same exact steps of like logic that you learned in lecture 3, and we're just putting it in like a new reaction context. Like all you're doing is acid-base, like protonation, deprotonation, proton transfers. You're doing a nucleophile attacking carbonyl. You're doing lone pair push, kicking something off. The other thing I will say is like going from here, this structure, to this structure, how many protons moved? How many hydrogens moved? How many do we add to the O minus? 2. How many do we remove from the nitrogen? 1. So 3 happened total. If you tried to do this and write proton transfer, we would have to take off a point. And it's because a proton transfer is specifically only for two protons moving, one of them a deprotonation, one of them protonation. And so it's just a specific thing with the notation that I want to make sure that you're aware of. Cool. I'm not really going to go through the hydrolysis of this right now, but it is the exact same process in reverse. So like the first step is different between the amine and enamine, and then it's exactly the same the rest of the way through. And you are just undoing what you did. Just like with learning the acetal hydrolysis and synthesis mechanisms, I think after the first exam, you'll have a good idea of what you personally need to do to study this so that you can recapitulate it. And I'm just kind of including this here as like a pretty reference. I will talk about the line reactions really quick. So to go from an amine or an enamine to the ketone aldehyde and kick off the amines, you need H3O+. And you need specifically H3O+ and not just like acid. So does anyone want to take a stab at why we need the H3O+? And maybe the highlighting here would give you a hint. Yeah, we need something that's going to have an oxygen so that we can add it and make the carbonyl. And so H3O+ has the oxygen. There's going to be a water molecule at this point right here that will go in and attack. Cool. So we are going to go and look at one of the problems on the P set that's amine, enamine. And it's kind of weird. So I'm not giving you an easy one to start with. What type of amine is this? Primary or secondary? Primary. It's just a one carbon thing. So a primary amine and a aldehyde, we would expect to make which one? An amine or an enamine? Amine, right? So we would expect to form an amine. And maybe I'm just going to go and draw what that amine looks like. I'm going to just do it on the left side for funsies. We would expect the amine to look like this, right? But what did we wind up with? Something weird and funky. What's a functional group in this? An enamine. So, something happened weird after we got here, where we are doing something with an enamine, and in fact, we're making two enamines. One here, and one here, like an enamine on either side. So, what we're going to do is I'm going to give you a couple minutes where I want you to draw the curved arrows to get to this structure, because that is going to be the straight up amine formation mechanism that is like in the lecture notes and the section notes. It's just kind of like regurgitating it. And then we are going to do the weird steps together to get from this thing to the final product. Just like 30 more seconds. Okay. So, I'm not gonna write it out or like put it up because it's on the answer key for the skill builders, and also it's just kind of copying down arrows, so it shouldn't be like crazy things happening. But I want y'all to like finish this on the problem set so you don't have to do it later. So I did want you to like try to write it out. So once we are at this step, this is the first time where we're going to have to look at this product and see what's kind of going on. Well, we know that we need to form a ring somehow. And so rings are typically formed by intramolecular reactions, where part of the molecule is attacking itself. And then enamines, you know that that's typically what functional groups coming together. For an enamine, what functional groups make an enamine? Sorry? Those are kind of analogous to each other, but I'm saying in the reaction that makes an enamine, what are the functional groups of our reagents? What? What type of amine? Secondary amine, okay. So this, we say, comes from a secondary amine and a ketone or aldehyde, just in terms of functional groups. So going back to the structure that I drew up here, kind of our first structure that we are going to start at together, we have an aldehyde, right? But do we have a secondary amine? Not really. We have an imine here, and then we have a primary amine. And this is the thing that's kind of weird. If you kind of blur your eyes and look at this thing, could you imagine that it's like a secondary amine like this? It has a lone pair. It's a nitrogen with a lone pair. This is the weird step where actually we are going to use an imine. We're going to use its lone pair to do an intramolecular attack and attack the carbonyl. So this is the type of step that, like, there are some steps where it's easy to draw the next molecule, right? Where you just like are adding an H or something. And there are some steps that are harder to draw the next molecule. So I'm going to show you a tool that I like to use to draw cyclic structures like this. So what I do is I just number all of the atoms that are going to be in the ring. So we know we have the carbon here, 2, 3, 4, and I'm going to call this nitrogen up top 5. So we know that we are going to form a 5-membered ring. And we know that one of the things in our 5-membered ring is going to be a nitrogen. So all I'm going to do is draw a pentagon and put a nitrogen on it. And then I'm going to worry about mapping everything else after that. So pentagon with a nitrogen. And then I put on my numbers. 5, 4, 3, 2, 1. So, what should we have at position 1 based on our previous structure? We should have an O with a negative charge, and then there's an H, which I can just imply on there. Then, do 2 and 3 have anything interesting going on? No, what should 4 have? Should have a double bond to the nitrogen. And then the nitrogen needs a methyl. And then our last check, do we need any charges? Where? Nitrogen should have a positive charge. So that's how we can do a tricky kind of redrawing thing. And the people who are doing it quickly in their head, or like if you see a professor doing it, they are doing this process, they've just stopped writing it out. And so when you're first doing it, write it out. It's the helpful way, it's how everyone kind of sees how to do this. Okay, so now let's maybe deal with some of these charges. So why don't we neutralize this oxygen and grab an H+. And then we have this kind of iminium thing where we're wanting to make it neutral. And so what is the way that we had to make an iminium neutral in the mechanisms that we saw earlier? We can't deprotonate anything on the nitrogen, right? Because it doesn't have any hydrogens. So what do we need to do? We do an alpha deprotonation. So I'm going to list out the numbers again here. So the 5, 1, 2, 3, 4. Which of these are an alpha position to our imine? So the correct answer is 3, because it's the carbon one away from the carbon in the imine. 4 is the carbon of the imine, so it's not the alpha position, it's not the neighbor one. 1 is not the alpha position because it's connected to the nitrogen, not the carbon. So we are going to, on this alpha position, draw out one of the hydrogens explicitly. And then I'm going to use just sol as solvent, something with solvent. You can use water, you can use another amine, whatever. This abbreviation sol, I'm pretty sure y'all can use. I just need to check with Tim once he gets back because he just didn't introduce it for whatever reason in lecture 3 when he normally does. So we are going to have it deprotonate this alpha position, push the electrons in and form a carbon-carbon double bond, and push the electrons in the imine bond up to the nitrogen. And hey, we've made one of our enamines. Now we just need to make the other enamine. So going from here to here, I think that we are going to be needing to make a double bond here. Do you agree? Like that is the position that we need to make the double bond? So if that's the case, what do we need to remove from this molecule to get a double bond there? The OH. Anything else we need to remove? A hydrogen. Specifically here, we have 2 hydrogens. And up here, we only have 1 hydrogen on each side. So we need to remove the OH and remove a hydrogen. Why don't we start with the OH, since that one looks kind of more immediate. What functional group is this? It's sneaky, it snuck up on us. We didn't even know that we made a functional group. We were just drawing the thing, and there's a functional group. It's the hemiaminal. She pops up everywhere. She pops up everywhere in these reactions. So, what we did with the hemiaminal previously is this is the way station right before we kick off water. So if we go back to the general mechanism here where we saw hemiaminal, we protonated it, and then we did a lone pair push from the nitrogen and kicked off water. Bless you. So let's do that exact same process of protonate the oxygen in the hemiaminal and then kick off water. Get really good at drawing polygons in this class. So, yet again, we reached an impasse where we formed this iminium-like structure. So what do you think that we should do to make it neutral? What did we do earlier when we had this iminium-like structure and we were trying to neutralize it? I heard some mumbling that I think the mumbling was alpha deprotonation. That's exact one. So again, we have our C in double bond, we go 1 over, it's the alpha position, and then we are going to take off a hydrogen on that position. I'm just going to use something as a solvent. And that will take us directly to the product. So this is like an exam level kind of tricky amine enamine question. This is not the most straightforward. It has part of it, this whole first section of the mechanism, that is just regurgitating it. And then the weirdest part of this whole reaction is this one step. Because once you do this, each one of these other steps are things that you have seen before. They are protonations, they are alpha deprotonations, and then they are a lone pair push kicking off water. So that's going to be kind of the skill of, we give you these new reactions and having you kind of take them and internalize them and be able to use those moves when we give you a weird reaction. You will not need to do weird things for every reaction. Like for a line reaction, a box problem, you wouldn't be doing weird stuff like this. This is only for a mechanism question. Okay. Cool. Well, that's amines and enamines for today. Let's go on to topic 3, which is our redox line reactions. So do y'all remember in Gen Chem doing oxidation number? Or vaguely, like, there were these rules that you'd remember of, like, hydrogen's always +1, and then oxygen's usually -2, and there was this whole system for Gen Chem. You don't need to know any of that for this, because organic chemists are lazy, and we want a really easy system that we can just, like, count to 5, or count to 4, really. So we use a system called the oxidation level system, and it's a way of telling the oxidation level of a carbon. The oxidation level is the number of bonds that a carbon has to electronegative elements. So alcohols, amines, alkyl chlorides, or alkyl halides, these are all oxidation level 1 because there's one bond to an electronegative thing. Ketones and aldehydes are oxidation level 2, and you saw them react previously. Oxidation level 3 are the carboxylic acid derivative family, and that's the kind of other big reaction family of this lecture. And oxidation level 4, you really only encounter 2 things. You encounter CO2 and carbonic acid. Why are we telling you this? Why do we care about it? So it's because things that are at the same oxidation level undergo similar reactions. Like, do you remember in lecture 3 how all of the reactions that we did, you could start with a ketone or an aldehyde? It's because they react really similarly. Likewise, all of the CADs react very similarly and do very similar reactions. And you haven't learned it yet, but an alcohol and amine do similar reactions, as we kind of saw with, like, translating the amine kind of onto what we were doing. So that is why we care, because it's going to tell us something about the reactivity. But the big thing for this, like, section of the notes is we need to learn how to move between these families of oxidation levels. So if we go up oxidation levels, we say that we're doing an oxidation reaction. And if we go down oxidation levels, we say that we're doing a reduction. So if I go from level 2 to level 4, did I do an oxidation or reduction? Great. If I went to 3 to 1, what did I do? Reduction. Cool. So we call those redox reactions, ones that change the oxidation level of a carbon. So let's meet the players here that are going to be helping us out with the redox reactions. So first up, for oxidation, we have chromium trioxide. And you know, she's sleek, she's elegant, she's symmetric. You might find her walking New York Fashion Week. She has some sidekicks that she carries with her. One is pyridine, which is just a basic solvent, and you can abbreviate with PYR. The other one's water. And she is going to handle the oxidation side of redox anytime we need to go up oxidation level. And then the bad boy, you know, walking the runway. You know him, you love him, lithium aluminum hydride. You saw him in lecture 3. Lithium aluminum hydride is going to be adding hydrogens to things. And when it does that, it's going to be removing some of those bonds to electronegative elements. Now, I know that this is going to feel a little bit crazy, but these reactions are going to do a lot of heavy lifting in this class, and we are going to use them a lot. So could we just take a moment and give them a round of applause? Thank you. Thank you. Don't forget them. You will, these are going to be the reactions that you use the most in line reactions going forward. So, let's get into it. What are the oxidation levels of all of these reagents? Can you show up on your fingers? What's the oxidation level of all of these? So all of these, the carbon has one bond to something that's electronegative. So all of these are oxidation level 1. The 1' and 2' have to do with like the classification of the alcohol of like, is it attached to a primary carbon or a secondary carbon? Okay, what's the oxidation level of a ketone or aldehyde? 2. And so we go up in oxidation level, we know that these are oxidations. And then what about a carboxylic acid? What's its level? 3. Great. So one thing that you'll notice here is that the sidekick for chromium, when we go up 1 level, is pyridine. But when we go up 2 levels, our sidekick is H2O. Does anyone want to take a stab at why we need H2O if we're going to go all the way to a carboxylic acid? You need an oxygen, right? Like over here, you are turning this oxygen into a carbonyl, right? So you don't need an additional oxygen. But here, you're turning it into a carbonyl, and you also need to add another oxygen on top of it. And because of that, we use water as the sidekick. Now, for none of these, do you need to know the mechanism. For all of these, you just do as a line reaction. And so I would like recommend thinking of like a little storyline or like a little fake mechanism for you. Like I think of chromium as the hydrogen gobbler, where it'll gobble up a hydrogen and make a double bond. And it's kind of stupid, but it works. And like you can remember it. Yes? Y'all won't. Yeah, so there are some like scarier oxidizers. Like you know how lithium aluminum hydride we said reacts with everything? There are scarier oxidizers than chromium that will react with things like permanganate. She pops off. She does things where I'm like, oh, that's scary. Like I don't want to work with permanganate in the lab. There's also, like, if you wanted to just, like, start off with an aldehyde and go from this aldehyde to this carboxylic acid, you could use chromium with H2O. And that's how we can get all the way to oxidation level 3. And so this is an intermediate here, but I think it's just explicitly useful to show y'all, because I think that there are some reactions where you will need to know that you can go from an aldehyde to a carboxylic acid. Now, the reductions, lithium aluminum hydride, you've done mechanisms with her before. But these mechanisms are tricky, and they do things that we don't really want to get into for this class that are not the most relevant. Like the lithium is going to like become a counter ion to the O-, and you're not going to neutralize it, and then aluminum like associates with it. That's beyond what we're going to do. So again, I like to think of it as like the hydrogen fairy that goes around and like drops hydrogens on things. It'll take carboxylic acids, amides, and nitriles, which all of these are at oxidation level what? 3, they're all in the CAD family. And it's all taking them to these products that are oxidation level what? 1, alcohol and amines. So all of these are reductions. The other thing I want to just flag here is these 2 reactions right here are the only reactions in this entire course, the whole summer, that will result in an amine. So if you are doing a box problem or a synthesis and you see an amine in the product, you know it must have been one of these 2 reactions. You will want to remember that for the future. Maybe even for 20 minutes from now. Who knows? So let's do some practice with these line reactions because, again, we're not doing any kind of mechanism associated with these. So I pulled 3 to work on. These are from Challenge Problem 3 and also Skill Builders, page 6. And these are going to do some oxidation level moving. Like they all involve a redox reaction. And then they're going to involve some things that we have seen from like lecture 3 or from like amine enamine stuff. Like what functional group is this? Acetal. So we're going to do some sort of redox and then acetal reaction. What functional group is this? Enamine. I know that the names are like new, but this is why I'm like, yes, this is a thing that you will want to learn. Okay, so take a few minutes and try out these 3 here on the left. I opened Instagram and a video started playing. I'm so sorry for your bad nickname of Jan. But I know it's Jason now, but I was just, I never called that name.
It sticks. Oh my god. I could also bring one. Alright, let's bring it. I could do it. I'll do it with you, even though it's faster. There you go. I think you use LIA. Will that give the
So, think about it this way. There's both some oxidation levels. So your first step is not going to necessarily be a redox that makes a carboxylic acid, right? Actually, I think everyone's struggling with this. Can we talk about the first one? So, this one's kind of tricky because what's the oxidation level on the left? And then the right? Well, each of them, we do it for specific carbons, so 2 of them that are 3. So we didn't necessarily do a redox first, or like, it's not clear that we're just going to do like one step and become here. And so maybe let's use the fact that we know that a redox reaction is going to happen and say, what could this product have been before we made carboxylic acids in the end? Because we now know that we could make a carboxylic acid out of some other functional groups. So what could those functional groups have been? What? Alcohols or aldehydes? Let's go with alcohols and see what we notice. So we know that we could just oxidize this with H2O, turn it into the top one. So how do we go from here to here? That's the question. So we definitely need to open the ring, and we have an ester, and what's the first thing you should think with esters? Thank you. Thank you. I love Pavlovian conditioning. So going from here to here, like maybe one of these O's is one of these O's, and one of these O's is this. So that means that this carbon, let's say, is like that carbon. What did we add to that carbon? Hydrogens, right? Like now it has 2 hydrogens, double addition. So we need to add hydride, double addition. What should we use? Lithium aluminum hydride, otherwise known as toxic masculinity. With H plus workup. Or what? Strong boy. Soft boy and strong boy? Soft boy and strong boy? Okay. Weak boy. Okay, wow. So that is going to take us 1 and 2 to this structure. And then to go from alcohols to carboxylic acids, we know we're doing oxidation of chromium, and we have to have H2O because we're going all the way to oxidation level 3. So that's how to approach one like this. And then I saw some people skip ahead and like work on this one. So here we have an acetal in the product, right? Well, one of the tricks that we learned is anytime we see an acetal in the product, why don't we disconnect and see what came right before it? Because we only know one reaction that makes an acetal. So what should we have there in the place of where the acetal was? A carbonyl. And then we had this alcohol before. So again, we're using our disconnection tools. These are going to be used more and more often with this types of problem. So how do we get from this structure to that one? Are we changing oxidation levels? Yeah, are we doing oxidation or reduction? Oxidation, so we use chromium. And then do we use pyridine or H2O? Pyridine, because we're just going from oxidation level 1 to 2. Okay, and then the next part of this is an exam 1 like question where we're forming acetal. So we need to supply our alcohol because that appears in the product, and we need H+. No step 3. Cool. Third one here. What functional group do we have in the product? An enamine. Okay. Well, why don't we try the same strategy that we've done with all of these? Maybe these were selected because we should be doing this backwards thinking on all of these. Pattern. I don't know. So we only know one reaction that makes an enamine. Let's try to do our synthetic disconnection. So remember back when we talked about it over here at the very beginning, we were like, okay, to do this disconnection and go backwards, we should cut the bond with the nitrogen, put a little H, and then in its place have a double bond O and make everything a single bond on the side. Can you try to do this disconnection with that problem that we were just looking at? So you cut the bond to the nitrogen, add a little H on it, replace the nitrogen with a double bond O, and then make things single bonds on the side. Bloop. So we have this, and then we had a hydrogen there initially, and so this is actually like an aldehyde. How'd you deal with the disconnection on this one? I know it's kind of tricky when first learning it. It's just a thing to practice, and I think now you know to practice it, and you know how important it's going to be. Okay, so now how do we go from this to this? Yeah, we're just doing an oxidation just like in the one right before. So we're going to oxidize this to an aldehyde. And then we're going to do the enamine formation by just adding our amine. And then you can, if you want, write pH around 5, but we're not going to grade that. Like, you're not going to see it on the problem sets. Yeah. It's like a very controversial thing among like organic chemistry textbooks and teachers, and I just think it's so boring. Cool. Yeah.
Does the oxidation or redox reactions have to happen for all the steps?
Yeah. Yeah. Like here we reduced it down to oxidation level 1, then oxidized it back up to oxidation level 3. So you'll see it in very different formats. Yeah. But that is redox. We will use it a lot, probably more than any other reaction. They're removing the chairs again. What are they Are they throwing another dance? It's going to look like a prison.
Because we have to work it out.
Gosh. Wow. Okay. So let's move on to topic 4, the CAD reactions. So this was a lot in lecture and it was kind of spread out. So I want to kind of hit some key points of what you need to know and understand. So first, I kind of like typed up and yassified a little bit this page from lecture. The big thing that you need to know is you need to know which of the CADs are more or less reactive. You need to know this order down cold. So, and you can actually even skip acid anhydride and carboxylate. You need to know the order. Acid chloride is the most reactive, then esters and carboxylic acids are about the same, then amides below that, and then nitriles below that. That order is very important and you will be using it a lot. Now, the purpose of the whole family of reactions that you learned in lecture 5 with these CADs is just to interconvert from one CAD to another. So we have all these reactions, and I know Serenia is a chart person and I am a reaction web person. I just like visually looking at this rather than looking at a chart, but you can use whatever you want. These are reactions where you will have to do some memorization of the reagents. And I do not expect any of you to have that down, and I don't expect us to learn them right now. I'm presenting this as a tool of take my word, I've summarized things, these are the reagents that do these reactions. Let's use this as a tool. So one of the ways that this web was designed was that it is written in order of increasing reactivity. So the topmost one is the acid chloride, it's most reactive, then these, then this, then this. And then in order to kind of organize all of these reactions in a way that's going to be useful to us, you need to know 2 key facts. So the first key fact is that you can always go from a higher reactivity to lower reactivity. So acid chloride, you can go down to ester, you can go down to amide, you can go down to carboxylic acid. Nitrile, she's the weird cousin. She's still part of the family, she's invited to the reunion, but she doesn't follow all the rules. She only has her own kind of one reaction that she does. But generally, we are always okay to go down reactivity. But going up in reactivity is hard. So if I want to go from amide to ester, I don't have a one-line reaction that does that. If I want to go from amide to acid chloride, I don't have one-line reaction that does that. So that's kind of one of the constraints. We can always go down in reactivity, harder to go up. And then the second key fact that you need to know is that everything interconverts with carboxylic acid. So each one of these, and I tried to put the kind of first fact things in blue and then the second fact things in red, everything can become a carboxylic acid, and then a carboxylic acid can become everything except for the nitrile because she's weird. So let's say I had a box problem where I was trying to go from an amide to an acid chloride. Can I do that directly? No, because I'm going up in reactivity. But I can go from this into a carboxylic acid and use that, and then I can go from a carboxylic acid to anything, and then go to the acid chloride. So that's the logic that you are going to be using for these types of reactions, and I'm going to let you do some box problem practice of this in a minute. But truly don't think harder than that. Look at the starting materials and products, say, did I go up or down in reactivity? If I'm going down, I can probably do it directly in one step. If I'm going up, I'll probably need to go to carboxylic acid, then go to it. It's not deeper than that. It's not deeper than that. The other notes that I'll give is the mechanisms are fair game. Like, they are fair game, and the thing is, they're just not that interesting, and we don't test it a lot. Like, the nitrile hydrolysis mechanism we've tested before, but I don't think we've ever done just like a Fischer esterification as like an exam 2 mechanism. Mostly because all of the steps for these reactions are so dang similar to the lecture 3 stuff. And so I think a lot of times for us when we're writing the exam, we assume if you could do a mechanism for lecture 3, you can do these mechanisms as well. And it's just kind of themes and variations here. And like the core idea at the reaction that's happening here is you have a carbonyl with a leaving group that a nucleophile is going to attack. It might be in base, might be in acid. You get to a tetrahedral intermediate where sometimes you do a lone pair push and kick off a leaving group. And then now you're a new functional group. And like again, protonation states are weird. You have like proton transfers and things. But like this is the fundamental idea behind all those reactions. And to help you with studying the mechanisms, which you still should do, I have made another reaction summary sheet. It is a trap. This is a trap. Please work through these, study these mechanisms on your own. But I grouped them into the simple CAD hydrolysis ones, which all of these have really similar mechanisms. The simple CAD syntheses, that these have similar mechanisms. And then the two that have weird mechanisms of the acid chloride synthesis. It had this kind of like super lone pair push thing where you like pushed up, pushed over, pushed out, and then kicked off an SO2 gas. That's a lot. Like, that's weird. We've never asked students to do that on an exam. So it's kind of like, yeah, learn it, but also it's much more common to see these family of reactions as line reactions. So like the tool that I think will be much more helpful is this reaction web rather than the whole like reaction summary sheet. Okay, with that, let's look at the practice. So this is practice number 3. This is taken from challenge problems 3 and 4 in Skill Builders, page 6. And what I think I'm actually going to do is I'm going to say, make sure you find these on the section handout, and I'm going to leave up the web for you to use. Because I don't expect you to have any of those reactions memorized, but I think that it's important to just be able to look at the line reactions and be like, am I going up and down? And then pull the reagents that you need from the reaction web.
And that was enough. No, I went to sleep like 10:30. Cause did you keep waking up too? I was I found out on Facebook Marketplace for Friday course, so I texted the girl, I was like, can I come get this today? I'll be there. We're gonna be sleeping so well from here.
So you make purpose of coffee first, and then for making that, you need to apply the right up. So got the bond there, and what's the alcohol? Where did you put it?
Any students who need to.
So all of these
Yes.
are carbonyls, and then something on the side.
Yeah.
So you should cut the bond between the carbonyls. Yep. So what's that alcohol?
I was like, I'll talk to you soon at the Monday meeting, these are all follow up.
Yeah, it's ethanol. It's an OH with two carbons with alcohol.
There's not.
And then you're done.
So you just add.
Oh,
COH
there's no
after
step.
An H plus.
I was like, I really.
Yeah, like step 2 of EKH plus.
So just to make sure the R
I just-
on those reagents
Just, I could
And
only
how
have
do you
like
count
that.
it? Yes, and you want to figure out what is the specific R that adds these two carbons.
So you said so we're yeah, so we'll move this. So we're gonna have to flip the protein after we're gonna create this. So we don't want OH, we want ethyl.
Yeah, the way I would recommend splitting it is put it between the carbonyls and then the yes.
But then that O is the same O as the carboxylic acid. Right? We're not gonna add the O.
Oh, I
No, so that when you do the mechanism, you will see that it's actually a different O. This O is going to be alcohol.
And also we're gonna add ethanol.
Yes.
Oh, okay, so I know. That's why it says OH here, so I just have to
Yes.
here is
Wait, you use good tests, right?
Yeah.
I've seen several people now doing the scribble to erase thing.
Yeah, so good.
Is that a setting that I have to enable?
It's inside.
What? If this just works, I'm gonna scream. So let's say blah. Yeah, no.
I will see.
I don't know, who's wrong?
Oh, so go to 10 settings.
10 settings.
Go down, I think. No,
Do I just have like an old version or something?
maybe. What's wrong with that? No, because I have a 10 settings.
Oh, wait, no, I'm sorry.
I might need to update it. Is that new?
I have had it since I got it like earlier this year. So I don't know.
Huh.
It's very good.
Okay. Let's talk through some of these. We maybe should not take the time to talk through all of them. So, were there any that people thought were tricky that they want to do?
The bottom one?
Yeah.
The bottom one, yeah. Okay.
Yeah, bottom two.
Yeah, let's do the bottom two. Let's do the one before it first. So, what functional group did we start with? Great. What did we end with? An amine. We only know for this class 2 ways to form an amine. Oh, if only I could remember. If only I was given warning to remember which reactions make amines. So, gosh, what reaction could we use? I like seeing everyone just scrolling. A reduction, lithium aluminum hydride. Okay. And then what type of amine is this? Primary, secondary, or tertiary? Tertiary. And if you look back at the reduction reactions, one of them only makes primary amines, right? So which one only makes primary amines? The reduction of what functional group? Yeah, so if we did the nitrile reduction, we would wind up with a primary amine. So did we do a nitrile reduction here? No. So the only thing in the world for this class that this could have come from is an amide. Like the two options, 2 ways of making amines for this class are to reduce an amide or to reduce a nitrile. Nitriles only make primary amines. This is not a primary amine, so we must have had an amide. And so all we do is put on the carbonyl. Yeah. So it's the classification of an amine is based on how many carbons it's attached to. So it's attached to one carbon thing over here, one carbon thing over here, one over here. They're tertiary. So now this is a CAD question. Can we go directly from a acid chloride to an amide? Yeah, why? We're going down in reactivity, and that's our key idea. We can always go down in reactivity directly. So what we're going to do is we are going to disconnect the side chain, and this is always the spot where we're going to want to disconnect for CAD reactions to kind of figure out what we added. And so our amine that we want is this one right here. And we can either use this with pyridine, or the other one that's on the chart is we could just use this, but in excess. And so you just have like more of it, and it'll act as a base. And that's what pyridine does in the reaction. It just acts as a base. Okay, so that's going to take us here. And then to do the last bit, to do the reduction, we use our lithium aluminum hydride. Cool. Okay, bottom one. Where did you see HNET2 or HN something and DCC on the chart? For those of you who looked. Yeah, so DCC is this kind of magic coupling reagent that will take an OH and an amine and just plug the amine onto where the OH was. It just replaces the OH of a carboxylic acid with an amine. So if we are going to use DCC with this carboxylic acid, we're going to have the same like left side of it, but then we're going to replace it with NET2. So I'm just going to draw out the two ethyls here. Bless you. So that's going to be step one. And then this is now what functional group? An amide. And what happens when we use lithium aluminum hydride on an amide? We make an amine. We reduce. And this is the reduction that feels kind of weird, and this is why we don't ask you to do the mechanism. The reduction just looks like erasing the carbonyl for the reduction of an amide to an amine. So what we wind up with is this triethyl amine. So NET3. And this is like a common base that you'll see a lot. But I actually like a kind of cousin of this. This is not part of the question. But it's a nitrogen with 4 amines on it. It looks like a happy dude little dancing. And so we call this tetraethyl ammonium man. Or it's called tetraethyl ammonium, and then it looks like a little man. So tetraethyl ammonium man. Woo, I'm an amine. Cool. So that's kind of the big thing that you're going to see with CAD reactions and that you're going to do for other problem set things. Again, the mechanisms you are responsible for, we don't test as much, and is kind of logic that you've seen before. So let's wrap up the section today with the last topic of amino acid chemistry. So you've all heard about amino acids in classes before this, but now you have more of an appreciation of what these chemical groups actually are, of the amino group and the carboxylic acid group. And you know some reactions with them. At pH of 7 in the cells, or 7.4, it's in this Svita ion form, where there's a positive charge and a negative charge on the same molecule. That's just what that means. So there are a couple things that you need to learn with amino acids from this organic chemistry class. You are going to need to learn 1, how to build an amino acid, and 2, how to join together amino acids. So the way that we make an amino acid is we can make an amino acid from an aldehyde using this process called the Strecker amino acid synthesis. So the Strecker synthesis combines a few reactions that you have already seen in this lecture so far, but does it in kind of an interesting way to kind of stack them together. So the first step is NaCN and NH4Cl to the aldehyde. And this NH4 it's like a positively charged nitrogen thing. This is going to do an imine formation with the carbonyl, and it's going to make this imine. So it's not even a like primary amine. This is just fully ammonium, but it's going to do the imine reaction, exact same arrows. But then what's going to happen is cyanide here, CN minus, is going to come and attack and make this tetrahedral intermediate. So already going from an aldehyde to this intermediate, the alpha aminonitrile, we've installed the amino group of our amino acid, and we've installed a nitrile, and then we want to turn that nitrile into a carboxylic acid. And that is one of our CAD reactions. So you guys did do the arrow pushing and saw all the steps. I called it, I think, lecture 9 on the thing, or reaction 9. But this is just going to be turning this nitrile into a carboxylic acid, and that's this step 2. Step 3 is a little weird. It says neutralize. You can neutralize it to whatever level that you want, and it's only going to affect the protonation states of these side chains. So if you neutralize it to the level of cells, like pH 7, this is negative, this is positive. You could also have a version where you neutralized it in more acidic conditions where both of these are have hydrogens on them. Or you could do the version where like this is NH2 and it's like negative in NH2, the kind of deprotonated, more basic version. So there are many kind of forms that you can see this in. But you will always have some sort of neutralization step. It's just where you want to stop that neutralization is kind of up to you. Cool. So we talked about DCC. I kind of called her like a magic matchmaker that matches up the carboxylic acids and the amines and says kiss and makes amides. And that's all you need to know of it. Like her full government name is dicyclohexyl carbodiamide. You don't need to do anything with this. You don't need to know her. If you want to scratch this out and be like, don't ask, don't tell, please feel free. You won't be asked anything about it. You just need to be able to use it on the line reactions. So do you have any questions on the line reactions here of DCC, of what it's doing?
That's the only way you're going amino acids for this class?
Yes, yeah, for our class. This okay so far? It's about to get more complicated. So imagine I have 2 amino acids here, and I want to join, and I have these R groups, R1 and R2. And I want to join the carboxylic acid of amino acid 1, and I want to join the amine of amino acid number 2 together. And I want to get this product. Well, DCC is going to do that. It's going to put those together, but it's indiscriminate about the carboxylic acids and the amine groups. So it's going to glue these 2 together, but it's also going to glue the amine from amino acid number 1 and the carboxylic acid from amino acid number 2 together on these kind of ends, and then that's going to make this product. Or it could take 2 equivalents of this molecule and hook together 2 R2s, or hook together 2 R1s. And so there's just a lot of options here, and that's the issue. So if we use DCC with 2 peptides, we're going to get a lot of different products, and we only want to make 1. So our solution here is we need to do some protecting. We need to use this idea of synthetic protecting. Now, for exam 1, the only protection groups that you knew were you knew that you could protect a ketone or aldehyde as an acetal, right? So now we are going to learn how to protect an amine and how to protect a carboxylic acid. So to protect an amine, we use a reagent called BOC2O, and your notation is you're going to write BOC on that nitrogen. So it becomes NH-BOC. This is the protected version of an amine, and really what's going on in here is it's actually kind of stored as like a little amide, but all you need to do is be able to write BOC2O on an arrow and protect it. Then to remove it later, you use a compound called TFA. I've included the structures here as just like an FYI, but again, if you're like, don't tell me that, then feel free to exit that out. Now, so that's how you protect an amine with BOC. To protect a carboxylic acid, you turn it into an ester. So that is one of the reactions that you are responsible for and that you did learn earlier. You have a mechanism for it, and it's on the little web. But we protect carboxylic acids as esters. And then to deprotect it, we just go from an ester back to a carboxylic acid. So let's say we are trying to do this thing and we only want this product again. We would protect the amine over here with Bach. We would protect the carboxylic acid over here with ester. And then we would try it with DCC. And it only has one option for what to glue together. That would make this little peptide amide bond that we want. And so we've made the connection. We've done what we need to do with the protecting groups. So our final steps are going to be to remove those protecting groups and take them off. And here, the first step is TFA, which removes Bach. And then you can do an ester hydrolysis to a carboxylic acid. Now, that's a lot of like protecting, deprotecting DCC steps. Like there are 2 steps to protect, 1 step DCC, 3 steps deprotect. This is already 6 steps. Our syntheses that we're going to ask you are typically no more than 10 to 12 max. And so when you see a synthesis question that's a peptide like DCC synthesis, it should be pretty easy. Like half the reactions, you know structurally what you have to do. You have to do the protections, deprotections. There will for sure be a DCC question on either exam 2 or the final. And so if you don't see it on exam 2, expect it on the final. And again, it's typically the easier one. We also have like Bach chicken isn't real. Bach chicken can't hurt you. Bach. Meme. We have Bach, Afreamine, unwanted side reactions. So there are a couple of memes, but again, the memes were scant for this lecture. No, I found these. I have made there are some that I have found, and it's been too low resolution for me, and so I've gone back and made higher quality like typeset versions. And I'll be sure to note that when I'm like, I did put this into chemical notation software just for the joke. But with our last like 6 minutes, why don't we look at the challenge problem DCC synthesis and start to do some analysis on it. I was really trying to make it like worthwhile to come to section today because I know no one wants to right after the exam. So we have some starting materials here. And one of them is the amino acid glycine. We have something else as alcohol. And then our product, we have what looks to be kind of like a peptide, right? So we have kind of amino acid 1, amino acid 2, and this is our like peptide bond. So these kind of like, if you see anything amino acid, it's probably a DCC synthesis. So in terms of kind of structural things we need to do, this thing is not an amino acid yet, right? Like this thing with the benzene. So we need to think about how do you make this into an amino acid. So make an amino acid. And then we need to think about our kind of protecting, deprotecting stuff. So to help us think about the protections, let's look at our product here and let's do retrosynthesis. Let's go backwards. So if we were to draw what this product was right before we made the peptide bond, it would be, this side was the carboxylic acid, and the other side has the nitrogen. Like all I did with this step is I just split this into 2 things. And now DCC, again, we would have had to do some protecting, but this helps us kind of see where these molecules came from. Like this molecule very clearly came from here and we've done no changes, right? But we need to turn this thing into something that looks like this. Is there anything else weird that you noticed about this amino acid? What? Yeah, we have an amino and then we have an amide. It's not a carboxylic acid. But could we easily go between a carboxylic acid and amide as like truly the last step? Yeah, we can, because those are our CAD reactions. Those are the ones that we have our reaction web for. So at some point, we will need to turn this into an amide, and we know that that's on our radar. So maybe I'll just do amide. Whoop. Okay, let's think about how to make this thing into an amino acid. Well, what's our kind of method that we have for making amino acids? What was our strategy or our synthesis thing? The Strecker synthesis. And if we go back and look at it, what functional group did we have to start with for Strecker? An aldehyde. What functional group do we have? An alcohol. So this is still our kind of brainstorming. So Strecker needs aldehyde. Could we go from an alcohol to an aldehyde? What type of reaction is that? An oxidation. Because we're going from oxidation level 1 to level 2. So we use our chromium. CrO3 pyridine. So we've made an aldehyde. And then we can just straight up do the Strecker. So can someone look on the arrows and tell me what reagents I should use for the Strecker synthesis once I'm at an aldehyde? What reagent should I use for a Strecker synthesis? Can someone scroll to it and look at it? NH4Cl. Yeah. And that's going to make this intermediate where we've turned that aldehyde into a tetrahedral intermediate that has what on it? See? I'm saying, looking at the section notes of the Strecker synthesis, when we add this to an aldehyde, what should we have at this tetrahedral position? Intermediate. A CN and an amine. So NH2, CN. And then we should do, as our second step, the nitrile hydrolysis, which is what reagent? H3O plus, and then we're going to do some sort of neutralize. So what we're left with is phenyl here, NH2, and this is kind of tricky. You see we have this bond to CN, right? This C is a carbon that still is there, but that carbon is now the base of a carboxylic acid. So we have successfully turned this into an amino acid that's looking close to this thing. Now, what's the problem with, could I just do this, DCC, done? No. Protection. So, can we highlight here which sides we want to react with DCC from these two structures? On the glycine molecule, the one on the left, do we want the carboxylic acid to react or the amine to react? Yeah. So carboxylic acid, that means we need to protect the amine. Okay? And then on the other molecule, do we want the amine to react or do we want the carboxylic acid or amide side to react? We want the amine to react, which means we need to protect something over here. So let's do those protections. How do I protect the amine on glycine? Louder. Bach2O. The Bach chicken can't hurt you. So this becomes OH, carbonyl, NH, Bach. Do you want me to go 3 more minutes and finish this, or do you want to be done? Okay. So we have Bach2O, and then this one, we need to protect the carboxylic acid. What do we do to protect the carboxylic acid? We turn it into an ester. So what's your favorite alcohol? What? Sure, ethanol. ETOH, H plus. So we are going to have, and I'm going to kind of rotate this and write it looking like what we had before. So it's NH2, and we'll have OET here on the end instead of OH. So we've made our ester, and then we have our phenyl group off to the side. So we've protected, and we've kind of shut down this and this. So now we can combine with DCC. So I might actually write the word combine and DCC, or combine with DCC. And then we are just going to make the amide bond between them. So we have NH Bach over here. And then the position where the OH was, we now have our nitrogen. OET in the phenyl. And we still have our protecting groups on. So now we're like looking pretty close. We know we need to do some deep protections, and we still have to deal with this amide thing, right? So what order should we do? Should we deal with the amide side, or should we deep protect everything first? The amide first. The reason being is if we had this as like an OH, and then this is an amine, and then we tried to make an amide, you could just have another equivalent of this molecule as nitrogen to go and try to attack. So let's turn this into an amide. And if we look at our reaction web, how do we go from an ester to an amide? Yeah, we just add the amine with pyridine or just excess amine. Either one. I think on Serenia's she might have done it as like go to the carboxylic acid, then go over here. Either one works, but I like this because it's just one step. So let's add, what is our amine that we need to add on the end? NH2. So the free version of that's just ammonia, NH3. So we have NH3 in pyridine. And we're going to have the exact same molecule. With NH2 on the end. And then all we need to do to get our final product is deprotect. How do we deprotect Bach? TFA is the thing that removes Bach. Bach 2O puts it on, TFA takes it off. And just like that, we have a synthesis where, again, like so much of the structure of the synthesis was decided for us of we need to have 2 amino acids, we need to do protection and deprotection, and it's just working out the details of the specific reactions. Was this helpful in terms of like recapping the lecture and kind of seeing what's important? Cool. Try to take some breaks this weekend, rest. The problem set's due Monday. The quiz for lecture 5 is due tonight. It should be quick, the 3 attempts. If there are any issues, let me know. Email me. I'll be here for questions, but thank you for coming to section. Bye.
Do you have any tips if we want to like get this down?
Like all of lecture 5?
Yeah.
I would say treat mechanism study and line reaction study separately.
Okay.
And a lot of what I've done today for everything but the amines and amines, I've done very line reaction heavy.
Yeah.
And so use the materials I've made for studying line reactions, and then use the reaction summary sheet that has like mechanism details to help you with working through the mechanisms. Yeah. During? Yeah. You seem pretty on top of things, Georgia.
Thank you, Colton.
Yeah. See ya, Kate.
I took the first practice test and I got like a 4. I was like, oh, okay.
Dang. No, but I mean, that's what it's for.
Yeah.
It's like the tool for learning. At least.